Okay, it's time to start. It's the day 5 of stand-up winter lecture. Today's speaker is Professor Kun Soo from SNU, Industrial Engineering Department. He his background is industrial engineering, but during his career he went to KAIST Business School, and then he came back to industrial engineering department at SNU. So he knows the engineering area and business language as well. So please welcome him.
Okay. Thank you for having me here, and it's literally really great pleasure and honor to be here. And thank you for your invitation, Professor Lee. We have actually met around 17 years ago in 2009. So maybe I can talk a little bit about my connection with Professor Lee a little bit later when I introduce myself a little bit. Okay, here's a brief introduction before we start. So as he introduced, I graduated from Seoul National University Industrial Engineering Department, and now I'm a faculty member here. And before I go there, maybe I can point out. So I was a professor at KAIST College of Business for around 8 years before coming back to engineering department. But before going to the KAIST Business School, I was also in the finance industry. So I spent around 1.5 or 2 years in Bloomberg and Lehman Brothers. Probably some of you have heard about the company name Lehman Brothers. You know? Okay, it was not that famous before 2009 or 8, but nowadays everybody knows, but the company doesn't exist anymore. So this is the time period where I first met Professor Lee. He was also in New York, and I graduated from Columbia University Industrial Engineering Department. I got PhD there, and we went together somewhere in the conferences together, and then had a good relationship at the time. And it's been also around 7 years. The last time I visited POSTECH, I was in KAIST at the time, and it's really good to come back here and see some of you and Professor Lee here. So before I start, let me also briefly introduce some of the books I've written. I've written a supply chain management book, and around 2000, where is it? Around 2010, and it's been around the new edition and so on. And I've got several industry projects with many private and public institutions regarding inventory or regulation on logistics and so on, and supply chains. And these days I'm working actively on AI applications, especially for the reinforcement learning applications to the inventory or supply chain problems. And I'd like to introduce some of the ongoing projects of us. Well, not in the detail, but slightly about the content and the method that we are trying to use. What else? And here's another, recently I've written one book, sorry, Logistics and AI. And here I just talk about some of the industry trends or changes in direction with AI these days. Okay, so what are we going to do today? So I'd like to cover some of the classical theory and some recent AI applications for inventory problems, and we can just roughly divide the whole inventory problems into some of the single period simple problem, which has a famous name as Newsvendor problem. And the second stream is a multi-period and more positive lead time problem, which is a typical inventory problem, and a little bit harder than the simple Newsvendor problem to solve. And then we will cover another important topic regarding sourcing from multiple suppliers. And then suppliers uncertainty. In other words, some of the disruptions or yield uncertainties and so on, or lead time uncertainties and so on. So we will cover some of the sourcing part. And the last topic is about the multi-national inventory supply chain, meaning that the supply chain network consists of many different companies with different structures and complex structures. So we will cover how we can determine some of the optimal inventory level for all those various parts of the different problems. Before I go to the first slide, I'd like to make sure that you have downloaded some of the Excel file that I have given. So at some point of time, we will just practice a little bit with some simple theory to see what's going on. Okay, so the first topic is for the single period Newsvendor problem, and this comes from a famous newspaper industry, but let's just convert a little bit to a clothing industry these days because they have so much of similarity between the two industries. So what are the clothing industry? What are the obvious factors and unique features in this clothing industry? We have short selling season for most of the products. So if you have some coat or some of the paddings like that, it's most likely are sold in during the winter season. And most of the companies actually update their design and new features every year. So you can, if you are interested, you can see whether this a specific clothing or padding is in this year's edition or last year's edition or several years ago and so on. And the other unique feature is production occurs before the sales season. In other words, production of most of the coats or padding actually started not for this winter, but at least for last summer. So we are actually doing a quite hard business to determine how many products that we need because we are aiming to sell to the customer who are trying to buy any coats in the winter period, but our production should begin in the summer period. So it looks like it's quite challenging, but they are doing this business for many years. So they must have some of the know-hows. Without knowing these theoretical research, they have known their own knowledges. So let's just look for them and see what are the analytical results that we can derive from this structure. Oh, yeah. So this is the trend of the North Face padding. Some of you have had it or just have it even today, right? So North Face, this kind of padding was in a huge, quite famous and quite popular, especially in around 2010. Yeah, you remember exactly? Good. So it was something like 교복, right? And then it suddenly disappeared around 2015. And then it came back this year, North Face coming back again. So it has quite fluctuation. And once it's quite popular, almost everyone is trying to wear this padding jacket. So from the perspective of the company, they must have made a lot of money from this kind of huge success. But that's not always true because we have to make sure that the company has to have enough number of paddings before the customer is looking for those padding. So they have to know during the summer whether this padding would be huge success or huge failure. Depending on this result, sometimes the company is making a lot of money and sometimes the company is losing a lot of money. So outdoor padding revenues in Korea in 2011, it was $100 million. In 2012, it was even higher, and it was 140 million. But then it suddenly go down to 90 million in 2013. And you may wonder why such a huge decrease occurs in 2013. Honestly, I don't know. But we actually, at least we know that the fluctuation of this revenue is a unique feature of the clothing industry, and we can actually find similar trend in many other industries as well. But the clothing industry has a really high fluctuations in its sales. So what can we do? The value of unsold items. So what can we do with these unsold items or the inventories that are not successful in sales for the specific year? Well, these clothings are going to the other store that we call by, what is it? Outlet store, yes. And we got around 50% or even 80% or 90% of the discount if you go to the outlet store. So do you always go to the outlet store to buy your padding? Part of you, right? But it's not guaranteed that you can find what you want to buy in the outlet store. So what's the disadvantage of going to the outlet store? So the good thing about it is you can definitely buy it at a quite low price. But the bad thing is sometimes you cannot find out your style, your size, your color. So the availability is another concern for you. But except this availability, if you just think about the price, you should go to the outlet store, definitely. But this can be a huge headache for this clothing company because they don't want to sell this padding at a low price. So they want to know, they actually do not want to have any remainings, but it's almost impossible. And the other one is shortage, obviously, right? If too many customers are coming to the store and they find that no inventory, no padding is remaining, then that's actually a good story for the company. But it's not always really good because if the company had a little bit more of those paddings in production, then they can make a lot higher money. And it's quite important because from the history, you see that the padding sales is not always quite high. So you really have to make a lot of money when your clothing with specific padding is in a good success. Because otherwise in the next year, you may lose a lot of money from your style because the customer do not want to buy those styles. So you really have to make sure that you can make a lot of money or the money, all the potential money you can make as much as possible for 1 year in order to avoid any failure in the upcoming years. So for the clothing company, a important objective is to survive each year because if you survive the bad year, then at some point of time, you may be able to make some money. So this is some of the articles. So it really depends on the temperature actually of the winter. So winter padding is quite heavily related to the temperature of the winter times. These days it's quite cold, and if you don't have any padding jacket, you may want to buy it. But if the winter, sometimes the winter is not that cold, and you find the winter jacket is not that necessary. So if the company can estimate the temperature of the winter time, average temperature of the winter time during the summertime, it would be the best. But it already sounds quite challenging, right? Okay, so maybe we can go to one example to understand what's going on and what we can do to navigate or to mitigate this customer demand uncertainty. So let's just assume that we have just one single selling period. In other words, one specific period of time that we can sell specific design of the clothing. So here we just switch the topic a little bit, and then we now go to the specific swimming suits. Are you familiar with these swimming suits? Probably not. Yep. This is not for casual swimming because it covers your upper body and lower body together. Right? This is a specific purpose. Basically, this is for surfing. Yeah, last year I was in San Diego and many people wear those jackets when they go to the surfing in the ocean, by the way. Is it possible for you to go to the East Sea from Pohang for surfing? Yeah, some people may do that. So the reason that this covers all of your body is just because this swimming or no surfing suit is designed to protect your temperature from the cold sea temperature, right? Anyway, I didn't know that, but this is O'Neill is a quite famous company for that. And this company is even updating its design every year. So they know what year's design is this. So they are updating it every year. And let's just go to the timeline of this production. This is a quite famous story. So some of you may already heard about it, but let's just review it. So basically, the company thinks that this, by the way, thinks that the selling period of this swimming suit is from February to July. It's a little bit wide in terms of Korea, but don't be misunderstood because this is an example for the California, not for this Seoul or Pohang area. So it's a quite wide range of the selling season. But anyway, the production of those, for those selling seasons starts from October or November. So they need to determine how many of those swimming suits to produce on October or November. And then once they finish their order, the production begins and it takes around 3 months or 4 months. One of the reasons is the production occurs in Thailand. Thailand is quite far from California. So it takes around 1 month just for the logistics by the ship. And then they will receive their order around 3 months after their order. Yeah, they obtain all the produced swimsuits, and then when the selling season ends, then the leftover of units are discounted, and it basically goes to the outlet store. So that's the story. Each swimsuit sells for $1,818, so that's the regular price, and the production cost is around $110. So the simple calculation tells you that you can obtain $70 for each sales. If it's not sold, then this swimsuit goes to the outlet store at $90. So basically, you are losing how much? $20. So either you are obtaining $70 or losing $20. It's simple business. So the company should have been operating for a while, for many years. So they must have some idea of what to do. So the company have tried a lot of different styles each year, and then they got some forecasts from their own company. So you can assume any of the forecasting technique that either from your classroom or from your industry experience and so on. And then the company's actual demand is also recorded here. And at no year you can see a perfect match between forecast and actual sales. So it's either overestimation of the actual demand or underestimation of the actual demand. Here, forecast is 90, meaning that it's kind of underestimation. Forecast can be as high as 120, which means it's overestimation. So the error is recorded here in this row, and you can see a lot of different numbers. And these numbers are not directly applicable to your own decision of this year because the magnitude is not the same, and you don't know how many sales that you can make. So as you can simply normalize this value by taking the ratio between A and F. In other words, actual divided by forecast. Then you will have a simple one number, and which can be also used for any other new estimate, new forecast. So basically you have a number like 1.5 to 0.25. So it's between 0 and 2 roughly. So you have a quite big deviations from the actual for your forecast. So if you read those numbers, you have an idea that this company is doing really bad, right? But it's not really the story, because if you have a graph of those number, AF ratio, then you have a specific numbers that are quite off, either 0.5 or 1.5. But most of the numbers are actually around 1 from the 45-degree line. So the company is not really doing bad. And surprisingly, if you happen to get the average value of those number, this number, AF ratio, if you calculate the average is surprisingly 0.9976. It's too good, right? So it cannot be as good as like this 0.99. So that doesn't mean that the company is doing a perfect estimate, right? But how do we know that this company is not forecasting the actual sales perfectly? So the mean does not tell you whether the company is doing good or bad, because it's too good. So what you have to look for is the standard deviation. In other words, we have to look for the underlying variability of this forecasting error in order to really capture the magnitude of the errors that the company is making. So the standard deviation is 0.3, meaning that it's around 1/3 of the mean. So it's not small at all. So the company is making huge variation of their error, but on average, it's not bad. So what can we do? So the simple approach coming from this mean value is the following. Maybe since the average is good, maybe we can just follow the forecast as is without any modification, because on average it's good. But the second approach, second thought about this, maybe we can use this standard deviation and then use this information in order to make a better decision. So we will talk about how to make a better decision based on this standard deviation. So expected demand is quite good. So let's say that our new forecast of the swimsuit this year is around 3,200. And if you multiply this mean value, then you are expecting around the same value, 3,200. But the standard deviation is 1,181, which is quite high. So I want to use this information in my decision. Okay, in order to make the better decision, you have to first understand the cost structure of it. So we already know that if you happen to have a remaining, so product, it's produced but not sold eventually, then we will have a $20 of the loss. If you happen to have a too little amount of the products, then this is not actually a real cost, but you are kind of losing some opportunity to make more money. So let's say that it's a underage cost, and this cost is just 70, which is the same as the profit margin that we can make by selling it eventually. So in practice, this term is not actually directly appealing to the manager because it's kind of opportunity, because it's not real money that we are losing. We are kind of measuring it just a to be a symmetry, yeah, between the average and underage. We are kind of measuring this kind of cost. But after we have measured those average cost and underage cost, we have a clear idea that which one is better for us to have, either some remaining or shortage. So by comparing those two costs, clearly which one is better, which one to avoid. So underage cost is 70, overage cost is 20, meaning that overage cost is lower. So it's good to have some remaining. In other words, inventory. So shall we produce more than 3,200 or less than 3,200? Probably a better idea is more than 3,200 because you have a huge opportunity of increasing your profit. So basically, you can just increase your order size one by one and see what is going to happen on average. In other words, if you are just making one product in total, then the probability of selling this one product is almost 100% because on average, you have around 3,200 customers. So for the first product, you are almost able to sell it. So expected gain from it, which is the combination of the cost from selling it and also the probability of selling it is almost the same as 70 because you have a chance of selling it definitely and you have a amount of the profit margin is 70 exactly. And if you happen to have around 6,000 number of products, if you happen to have a 6,000 plus one more product, and those one more product is obviously would not sell eventually because it's too high, right? So the probability of selling it is almost zero, and you are losing $20 almost sure. But the numbers in the between, we have a certain trend of decreasing graph because as we have more and more product, our probability of selling it is decreasing. So that's one graph. The other graph is our probability of selling it is decreasing and the probability of losing, having some unsold item would be increasing. So eventually you have two graphs. One is decreasing, the other one is increasing according to the number of the product. And there must be a number where the two lines cross. Here, if you happen to make this number of product, your expected gain by making around 4,000 would be exactly the same as expected loss. But if you go a little bit left of those numbers, you find that the expected gain, the positive part, is higher than the expected loss, negative part. So it's good to increase your order quantity from the left-hand side. And from the right-hand side, your expected losses is higher than expected gain. So you should not produce that amount of number. So I got this number as an optimal order quantity. And as you see, this is much, much higher than 3,200, the average order average demand. It's even 800 higher than average demand. So probably if you happen to have around 4,000 number of a product in your production, and if you try to sell it, most likely you will have remaining. But that's not bad, because by having some remaining, you are kind of avoiding what? The shortage, right? Which is better. So let's just formally analyze it. Now it's time to use some of the mathematics. So each time, place an order to make the inventory position as S. So I want to know that I can, S is the order quantity that I want to make. And this is the level of the stock that I have. And after the demand is realized, I can either have two positions. The first one is positive remaining. So where the S minus D part is positive. The second part is shortage situation where S minus D becomes negative. And then I can assign two different costs. So for the first case where we have some of the remaining, I can multiply it with the average cost that I have defined before. And for the case of the shortage, I can multiply the cost of the underage. And then I will have a cost function for S and D. Here, I just put D as a variable, but actually, we cannot control this customer demand. So because of that, what I want to solve is not just GSD, but just a simple GS, which is the expected cost of GSD according to the random variable, the customer demand D. So that's eventually what I want to solve, and which is simply, so it's expected value CO S minus D positive, CU, D minus S positive, and I can divide it like this. Okay, I have to solve this. By the way, basically this is a function of S, so I have to control the S here and S there. So I have to find out the optimal value of this. So in order to solve it, I have to define this function because I have this part, S minus D positive, part of expectation, and D minus S part of the expectation. So expected value of S minus D and D minus S, something like that. So how can I solve those functions? Example, what is this? This is actually an integral from perspective of the D. We have from 0 to S of S minus D fx ft dd. dd 하니까 별로네. So let me change the value. S minus y fy dy. 이렇게 하네. The other one, D minus S positive will be from S to infinity, y minus S fy dy. So my GS now becomes CO 02 S of this, and 어쩌고저쩌고. So I have defined my GS here already, so I will not repeat it. So eventually what I want to do is the following. So I have this function here already. And then I want to get the derivative of this. So the question that I want to ask is, can you get the derivative of this? Yep. This is not a simple derivative. Why? 왜 그래요? Because we have S here and S here. Which one is harder to solve? S inside of the integral or S outside of the integral or both? So if you happen to have a S both in the integral part and inside of integral and also the range of the integral, then it becomes a little bit harder. So there are two strategies you can choose. First, you can either divide it one by one, or you can directly just get this derivative inside of it. This seems a bit abusing of mathematical term, but actually this works for this kind of specific form. This is not always true, so don't try to do that without understanding what's going on, okay? But for this specific example, I can just put it inside and we will obtain a simple equation like that. So it's going to be Fy from the calculation of it. So eventually what we have is here. So we have Fs. In other words, probability that the demand is less than S here multiplied by C0. And then the other one goes to probability that demand is higher than or equal to S. And then 이게 잘못. 아, 맞네. Yep. So everything is correct. And then eventually what we will have is this one. So in order to apply the first order condition, I have to make it as a 0 and I have to obtain the S. And I know that PD less than S must satisfy CU over C0 plus CU. This is what we call by a critical ratio. But anyway, this equation is not a simple one because my S is not a formula of this directly. In other words, my S is inside of the probability distribution. So in other words, in order to exactly obtain this S value, I need to know the distribution function of Fs. Then if I know this, then I would obtain inverse of the distribution function, but inverse of such distribution function is not always available in a closed form. So for example, if my F, the demand follows a well-known simple distribution like a uniform, probably I can find out the simple formulation for that. What else? But if you think about the normal distribution that are popularly used in practice and also in the class example, you don't have a formula for F. Because of that, you don't have a simple formula for F inverse. But numerically, don't worry, numerically you can do it, right? So basically what you are trying to do is the following. So you have a distribution, this is actually PDF. So you have a PDF. So this is not. So you have a distribution function like that. And what you want to find out is the value where the area is exactly CU over C0 plus CU. So numerically, you can generate any distribution function like normal. You have a, the normal table in the back of any statistical book, or you can use Excel to calculate it, or probably you would use Python. 맞나요? Can you? Okay. So the optimal base stock is available from the theory, or analytically, we know exactly how many parts to order. But there's some assumption, underlying assumption for this problem. First, we have to exactly measure the associated cost here, the C0 and CU. Sometimes these costs are not exactly available, especially for underage cost. It's not clear. Second, which is even harder for us to implement in practices, we have to know exactly the distribution of customer demand like this in a nice figure. So it doesn't have to be shaped like that, but anyway, we have to be able to draw this distribution function in a plot, which is not always available in practice. So due to those challenges, we know what to do, but actually we do not have enough information to implement this theory. So that's why in theory, but in practice, if you go to any workplace, most of the companies are not familiar with this Newsvendor theory and they are not implementing this. And if you happen to tell them that you have to have a inverse of distribution function, it's not easy to implement it, right? So it's elegant and classic and simple, but not that easy to implement. Okay. So there are several techniques to mitigate this kind of challenges. Okay. So I want to introduce those challenges. But before that, maybe we can just try some of the results with the Excel spreadsheet before we go. But we don't have enough time, so maybe let's come back to this spreadsheet a little bit later. So okay, so I have just proved that it's good to have S, and my S is determined by the inverse function of distribution function. But so we know how many products we need to have, but we don't know what kind of the rule that we have to implement in this situation exactly. So in other words, let's say that I have 100 products in my warehouse. Then what is my optimal decision? Is it still ordering S number of products as a new? Maybe not. So the equation actually tells you that you have to start from this number of stocks. So my S is not something that I have to order as a new. It really depends on how many products you have. And this just tells you that the S number is something that you have to have before the selling season starts. So this is what we call by a base stock or order up to level. But there could be other rules, like something like we have to fix the number of order like 100, 200. It doesn't depend on at all on how many products that we have. Sometimes this is true, or sometimes we have to be careful and we have to adjust our number according to some other situation like the demand or some of the other variables that we don't know. So still we don't know exactly which kind of the rule is optimal for this situation, but it's not difficult to prove it. So considering the material purchase cost, we can define the cost to go function of theta x. So what is my theta x? This is the total cost function that I can have eventually. And this gy is that the function that we already have. So gy has two parts, C0, expected value, S minus D positive, CU expected value, D minus S positive. So this is the GY function. And let's say that my current inventory position is X. So in other words, let's say that I have X number of products in my warehouse already. I have to decide my new level of the warehouse after ordering something. So my warehouse starts from the X value, and if I order something, then eventually it will go to Y. But Y is not the additional value. Y is actually the total number of the product after finishing my order. And I want to determine not just the number itself, but the rules to determining this Y. So how do I have to select my Y here? Coming from X. So this is a minimization problem, Y greater than or equal to X. And the cost of purchasing new product is determined by Y minus X, because this is the something that have to be newly added. And GY is the cost that are coming starting from Y. You may have some demand realization, and it can be either positive or negative. And depending on my leftover or stock out situation, you may be able to calculate the corresponding costs. So that's the GY. And how this function is minimized. I see that I can define another function. So rearranging this term, I see that CY plus GY is a function of Y. So I can take it as HY as a new function. And then CX is the other part. And here, my decision variable is Y, not X, right? Because of that, this is not relevant to my optimization at all. So how this HY is minimized? So it's good to have a plot of my HY here, because I know that my HY would be convex function. So how do I know that? Because CY is, this HY is a CY plus GY, and I know that this GY shaped like this. And this is a linear function. So HY would be another convex function. So I know that this point exists. So I can take it as S star. And this is the point where the derivative is 0. Now, be careful, because this is a minimization problem of Y, but there is a condition, because my Y should be always either higher or equal to X. So we can divide this into two. First, let's say that my X is here. Then what is my range of Y? Y should be any value greater than or equal to this. Then it's obvious to which Y would be minimized my H function, right? My H function is minimized by going into this. So if my X is less than S star, then my optimal Y is S star. Second case, if my X is here, what should I do? Yeah, I'm already in the lowest position that I can get. If I increase my Y value, I will getting worse off. Because of that, if X is greater than or equal to X, then my optimal Y is just X. So combining those two, I obtain that order only if your current position is less than or equal to S star. And how much to order? Exactly up to S star. So we have proved that this kind of the rule by not knowing the S star value exactly. Anyway, we know that such an S star exists. And then it's good to go there whenever we can go. And if we cannot go, we have to stay where we were. So that's what this policy structure tells us what to do. Yes. Still, we have solved a big problem by knowing that which structure is optimal for this problem. But that doesn't mean that we have already obtained my S star already. But for this simple problem, we know what to do because my S star is given here in this formulation. So as long as we know the distribution of the customer demand, we can implement it. What if we don't know the distribution? Can we obtain S star? By intuition? What kind of intuition? Good. Good to start. Yeah. Previous sales. Yes. So the second choice that I can rely on is obviously the sales data. In other words, if we don't have this app, at least we can use the data or some of the observations that we have, right? So that's why I gave you an Excel spreadsheet in order for you to practice the two things. First, let's assume that I know the distribution exactly. Then you can just apply this. That's the first method. And second, if you don't know the distribution, instead you may have certain observations and you can try to use those numbers for deriving your best order quantity. Okay, so let's just have a break, and when we come back, we can have a, no, we can actually do that, right? We have some time. Okay, so before we go, let's go for the Newsvendor workshop. So do you have this spreadsheet? Okay, let's just fill it out one by one. So can you determine here, the overage cost is 15, underage cost is 30, and let's just apply one order quantity, 2,500, and the demand is 2,000. In this case, which one is higher? The order quantity is higher. So in that case, you will have 500 remaining, right? Can you first calculate how many units are sold in this case regarding the order quantity and demand? Which one should you choose for the sales quantity? You realize that if the order quantity is 25,000, 100, and demand is 2,000, you can sell up to 2,000. And what if this is the opposite? Still 2,000. So can you generalize it? Yep. So simply, it's gonna be the minimum of those two. So it's minimum of order quantity and demand. By the way, I have already put some names of the cell. So because of that, it's just written in the text. So 2,000 is the sales quantity. And it's easy to determine units not sold and left. So it's gonna be max of my order quantity minus sales quantity, comma 0, right? Because it should be positive or 0 always. The other one, shortage. How do I know the shortage? It's gonna be another demand. No, this, yep, demand minus order quantity. No, that's the other. It's maximum of So yeah, demand minus order quantity comma 0, right? So this is going to be the underage and overage cost. So total overage cost will be CO times units not sold and left. What is total underage cost? CU multiplied by this. And summing up all those two, we will have eventually the total inventory cost. Are you following me so far? Quite simple. Now, this is the beginning. Okay. So I have a specific demand distribution like this, like 500, 1015, up to 4500. I have specific probability for each case. Then, how can I obtain my total inventory cost for specific order quantity and specific demand value? So in the top, I have specified the demand value, and in the side, I have specified the order quantity. I want to apply basically this case for different values of this one and different values of this one. So it's a combination of everything. So I can apply the function in Python. Probably I can easily obtain it, but in Excel, it's not easy to do that. But there is one way to do that in Excel more efficiently. Do you know how to do that? Well, what? Macro? Macro is good, but there is a built-in function. So let's just use it, okay? So select everything all together. You can do this kind of complex calculation by almost automatically, which is good. And go to the data, go to what if analysis, and go to data table. It's too small. And the row input cell, you can select what is changing in the row. Basically, that's demand. What is changing in the column? In this column, I am changing my order quantity. So I have chosen those two, and then magically all those numbers come out. But before you finish, you have to carefully check whether your number is correct or not. So do we have the correct number? So for example, my order quantity is only 500, but the sales go to 1,000. Are we having 15,000 in this case? Or that's too hard. So let's just verify this case. Order quantity 2,500, which is here, and demand 2,000, which is here. And do we have exactly 7,500 as my previous calculation? So which means I'm doing the right calculation for the all combinations at one time, which is good. Is it the end? Not yet. Why? Because we have just calculated my G, S, comma, D in this case. But eventually what we want to calculate is not G, S, comma, D. What we want to know, G of S. In other words, the expected value of those function, those costs. So I have to take the expected value of all these demand values, and I have a clue about it because I know the probabilities assigned for each case. So how can I calculate the expected inventory cost in this case for the order quantity of 500? I basically have to multiply this 500 and 0.05. 1,000, 0.05. So multiplication of those number and summation of everything in a row should be done here. And in Excel, you can actually easily calculate those values by using some product function, which is quite useful. So by using all those column here and the other probability column here, and then you obtain what you want. The good thing about it is you can just repeat this calculation here and there. So now you have every values here assigned, and then you have this one as the optimal value as. So 2500 seems to be the optimal choice that you have to take. So if you can assign some of the probability, instead of taking F inverse of something, you have this value. But you may also want to know what are the theoretical or analytical result and if those two numbers match. So I know that my CU over CO plus CU, which is the critical ratio, as 0.6666 something. Okay, then I need to find out the demand value where the F function, in other words, the cumulative distribution function, matches this value. So that's why I have calculated this cumulative probability. So here, analytical value, in order to find the analytical value, I need to look for the order quantity or the demand value, which exactly matches 0.66. But do we have such a number here in this table? Unfortunately, no. So we have to choose the closest one, but actually it tells us that either 2000 or 2500 would be the best number for it, but I will just skip it, but it's good to select always the higher value, not just the closest one, okay? So we will choose the number that is the smallest one above this critical ratio, which is obviously 2500. So theoretical value seems to match well with those my calculation. So this is one thing you may implement in practice if you happen to know the probability distribution. So which is a little bit easier because you don't want to take care of all those distribution function and inverse of it, which is quite tedious. So this is one way to do that. But that's not all, because there's another way to do that. And here, this is probably the thing that you may encounter in practice. You have a certain demand value, in other words, customer demand data. So how many of such data do we have in the second worksheet? I have, oh, that's quite a lot, right? And my computer is too small, too slow. We have around 1,000 number here, right? Okay, for each case of order the customer demand, we can calculate my inventory cost for each case. And then I can take the average. But we have to decide the optimal order quantity in calculating those costs. So here I have order quantity table from 500 to 4,500 as before. And then I want to apply this high row, the row value as my order quantity. And then I want to calculate my inventory cost here in case of customer demand of 2,500 and my order quantity is 500. So basically I can take the function here, but this function is quite spread over multiple columns. So you may not want to repeat this all of the separate calculation. So let's just directly calculate this at once. So basically I am multiplying CO and the overage cost is defined by maximum of something. What is it? Overage cost is order quantity minus customer demand. Isn't it too small? 너무 작아요? 없었다. Comma 0. So this is the overage cost part. And I have also underage cost part. CU multiplied by max of now demand minus order quantity, comma 0. So I want to repeat this for all of these cells. But in order for me to do that, I have to fix the row or column in order to copy it. So here, which one to fix in B8? I have to fix the row. So I have to fix the number 8 here. And in the A column, I have to fix the column as a A. So I have to fix A9, and also the same logic applies here. So I have to fix the row and fix the column here and there, and then I will obtain this function automatically. And then the remaining thing is copy it and paste it. Another thing, copy it and double click this small green square, and then I will obtain all the cost. Then, now I'm ready to obtain my average inventory cost for all these 1,000 data. So how do I get the average cost for the case of the 500 as my order quantity? I can simply take the average of all the costs. So here I select everything, and then this will have my average cost. And I can repeat this for here, and then I can obtain exactly almost the same graph as before. But here the difference is now I'm not assuming a distribution at all. I'm just using the data as is, right? So this is actually a kind of recent trend of using the data as is by not implementing or using the distribution function as in the middle, okay? So the reason that I'm introducing this kind of new worksheet is just because our new approaches to these Newsvendor problems are actually based on this kind of approach. So we are not working with the distribution assumption anymore, and let's just try to assume a numbers as is, and then try to update our optimal order quantity decision based on these numbers. So basically, I have two more questions that I want to ask to you. So if you're interested in, please solve this problem and let me know by the end of probably during the break time or during the lunch time. And then please get back to me. If you can handle those question 1 and question 2 and show it to me, then I can give you a prize. So volunteers will get rewards. Okay. So we have just covered this workshop for the demand uncertainty. So now we have covered the case of this certain probability structure. So if you happen to have this kind of table in practice, you can use it. But if you don't know, then you can directly go from the sales data and then obtain the same thing for the total inventory cost. So there are two questions. The first question that I want to ask you is, what happens if we think about the material purchase cost? In other words, let's say that I have to pay $15 for each of the products. Would this affect my optimal order quantity or not? If so, what is the new optimal order quantity? Second, make it slightly harder than that. So the company now offers a quantity discount. In other words, if your order quantity is more than 3,000, the company is giving you a discount. So the $15 purchase cost becomes $12 for the whole quantity. So if you happen to order 3,500, all of your 3,500 can be obtained at $12. But if you are buying 2,500 as before, then you have to pay $15. So those $3 difference may have an impact. So you can verify whether your new order quantity, whether you can find out new order quantity that can even decrease your inventory cost or not. So basically, you can work with the same Excel spreadsheet and to determine what's the best decision for you to take. So volunteers will get a free prize as a book. So you will see which book that I have after that. Okay, so we have covered this policy optimality. So before we finish, let me just explain the new approaches coming from this classical Newsvendor. By the way, this Newsvendor theorem has developed how many years ago? Around 100 years ago. So it's a quite old theory, but still useful. So the traditional approach, I can summarize it by model, data, and decision. In other words, I have a F as a distribution, and I'm working with this distribution in order to obtain something like this. So this is an example. And the new approach is two separate branches. The first one is the features. In other words, in my estimation, so basically, customer demand estimation, D, maybe if I can use more variables, more information for that, probably I can increase the quality of my estimation, and eventually that will reduce my standard deviation in our example. So I will talk about this a little bit later on. The second approach is what I just have told you before. Without this F distribution at all, I want to directly working with the observed number, observed customer demand, and directly I want to go to the optimal order quantity. So without assuming any model, without assuming any equation, I just want to know. So what happens if I order 2,500? What happens if I order 3,000, 3,500, and so on? So I can basically do some experiments. So by repeating these experiments for a long time, probably I have an idea which one would be the best one. So it's a kind of a simulation, right? Simulating my inventory cost for 500, 10,000. So it's basically just following what we have calculated in Excel in practice. So that's not actually quite elegant to me and probably to you, right? Because you have to do a lot of experiments, which is not good. But these days we have a good method to reduce the number of experiments for those kind of approach. So that's why we are trying to do so with the modern techniques. So here, the main technique that we have taken is basically AI-based technique. So to be more specific, it's the reinforcement learning. So basically, if you can apply the reinforcement learning, you can reduce the number of experiments sometimes, and sometimes you can get the number exactly without referring to a complex analytical analysis. But before the AI and all of those reinforcement learnings are quite famous, you have another big trend a few years ago. Do you remember? Before we are talking about AI, what were we talking about? as a big trend that are related to the features. Something about the data. So what do you remember about data? In front of the data, we have used, thank you. It was big data. So the previous buzzword was big data. You almost forgot. There was a time that everybody is talking about big data, SNS, and so on. Because of that, at those time periods, people are talking about a lot of big data related techniques. So those techniques are mainly used for increasing the efficiency or the accuracy of the estimation. So we will first talk about this and then talk about this. And in the middle of these two techniques, probably you will have some break. Okay, so let's briefly talk about the first data, first approach, feature-based data. So demand forecasting can be improved by using more features. So this is an example of demand forecasting for the tires for the car. Okay, so let me draw a car here, and this is the tire. So if you want to estimate the demand for these tires, probably these are very much related to the demand of car. So probably you may want to know how many cars are sold or is going to be sold in the future, right? Also, so you can divide this tire into the two parts. The first, used tire. Second, used tire. In other words, for the new car, you have a tire for every new car that are produced. So your tire demand, part of it belongs to the new car's tire. But the other one is for the used car. In other words, the car that you are already driving, there's some replacement time periods that are coming every 5 years or 6 years and so on. This must have depend on what? Your car sales of 5 years ago, right? So you have to look for the new cars demand and also around 5 years old of car demand in order to estimate this higher customer demand. And the first one is already quite complex one, but the second one for the replacement is even more complex because it's not mechanically, replacement is not mechanically occurring. Because even if you have spent 5 years, sometimes you find your tire very good. Sometimes if you're not lucky, you find your tire is not good in after 3 years. It really depends on your driving style, how long you're driving, and so on. The other fact is, even if you know that you have to replace your tire, you may not have enough money. In that case, you can say, okay, I can drive a little bit further, a little bit, which is happening to me. I can do it, I can do it, I can do it. So many years ago, I have used my tire too much, and then it basically just almost wear out completely. So the manager of the shop, when I take my car to the manager, he's very surprised. Oh, how can you drive this kind of tire like that? I told him that I didn't know, but in fact, maybe I knew it, but I didn't intend to, or I didn't have enough money to replace it. So many conditions are affecting my replacement decision. So that's, I would say that GDP, how good the economy is in overall. And there are many supplementary measures like education data, healthcare data, employment data, and so on that are supporting the economic situation, why is it important to consider education cost? Because education cost is competing with your spending on the car. If you're spending too much for your education, like your tuition, either your tuition or your kids' tuition. So anyway, if you're spending too much, then you don't have enough money. So employment is also important. Healthcare is another competing factor. So once you have more and more features, feature 1, feature 2, feature 3, and if you are estimating, here the estimation is basically done as a form of a regression. So you are not looking into a time series. Instead, you are just looking into the relationship between the factor and the resulting demand of the tire in this case. So then you can derive a lot of features like that. And sometimes the number of those features can be more than 100 or more than 1,000 in some cases. And it's getting even more complicated just because if you happen to pick up one feature, you can also think of a lot of time dimension. In other words, time lag. What is it? Sometimes you have an idea that GDP is important, but then you have to decide on history, which GDP you have to choose, either 6 months ago, 1 year ago, 5 years ago. So you can choose a lot of history of the GDP in order to apply GDP to your demand estimation. Then this 100 feature now suddenly becomes 10 to 3, 10 to 4, 10 to 5, and so on. And you cannot run regression with those number of features easily. So in the statistical techniques, people have developed a lot of useful tools in order to identify some of the essential features out of a lot of thousands or millions of features. So that's what is called by lasso. But anyway, we can say that as a big data technique. So by implementing this kind of technique, you are basically adding more features. So here's the result. So the company's benchmark is the error size is like that, and it's actually increasing as the forecasting horizon is increasing, because if you are going, forecasting horizon is increasing, your accuracy must decrease. And if you apply this lasso and with many features, these are the numbers that we have, and basically it's lower than the company's benchmark, which must be better than the other one. Otherwise, why do we have to see those papers and the graphs? It's good. And this is actually one of the techniques we have done, even just 5 or 6 years ago, not that long time ago. Okay? We have done this Newsvendor theorem more than 100 years. And this is quite recent technique compared to the 100 years. But we almost have forgot those kind of techniques already, because now we are going into the almost AI, reinforcement learning, machine learning, and so on, right? So that's what we have used so far. So as long as we have more features, obviously it's good. So in the Newsvendor, we have another counterpart of this one, which is called by feature-based Newsvendor. So what is the feature-based Newsvendor? So going into this demand, now I can regard this demand not just a random variable itself, but a function of certain features like the padding demand. We can characterize this demand for the winter padding as a function of the winter average cost, or winter minimum cost, minimum temperature, maximum temperature, and so on. So we can think of a lot of features like that. Or we can even make this demand of the winter padding as a function of GDP at that time, interest rate at that time. So we can use a lot of features in side of this demand, and depending on my estimation of those features, I can make it more accurate. And then probably I can make a better decision based on a more accurate characterization of my demand. So that was one big data approach that I told you before. And we can actually do the same thing with AI as well. So these days, even this kind of a many feature estimation, demand estimation with many features are done with AI. And the techniques regarding this one, we call it as machine learning. So basically, machine learning is used quite extensively for this kind of demand estimation, but the way they are doing is a little bit different. So do you remember what kind of task this machine learning is doing mainly or started? Probably you remember cat and dog. What is it? Yeah, image recognition or classification. Why is it useful for analyzing this time series? Image recognition. Because in this time series, we don't see any of the structure. But the machine learning can see some of the structure. So basically, what they are doing is quite similar. Just like they are recognizing cat and dog, they are recognizing some patterns in this demand. And then in the future, they decide what to implement among all the patterns they have collected. But the problem is we don't know which pattern the machine recognizes. The machine does not explain what kind of patterns they have found and what are the exact patterns they are implementing. But it's just takes an output as is, and we don't know what to do. But this turns out to be quite good. So we are using a lot of machine learning based technique, and this is one example of a convenience store product. There are so many products in the convenience store. So we happen to implement a lot of different machine learning based techniques, and some of them are quite good and some of them are not good. Anyway, these are the actual demand. So as you see, this demand is quite fluctuating a lot. So some products are sold during the weekdays. The other products are sold mostly sold during the weekends. And there must be some time periods, either in the morning time, either in the nighttime, and so on. So depending on the product characteristics, we will have certain different patterns of the time series of those demand. And because of that, we cannot just develop a simple, even for the machine learning, we cannot just apply the same machine learning technique for all those different patterns of the demand. It really depends on it depends on the techniques, specific techniques, either the, what is it, the support vector machine or what is it, the ensemble, and so on. There are so many techniques, so LSTM or many other techniques. Oh, yeah. It's already 11:05. Okay, so let me just go over one more slide. Okay, I have one more slide before I go. Okay, so these days, because of that, the companies like the big retailers like Walmart and you see Target, they are aggressively using the machine learning based demand forecasting in order to avoid product shortage. Okay, so I will talk about a little bit about this after the break. But anyway, this is a new trend, and we no longer kind of using the big data based technique frequently as before, because we have a good replacement. But we are now losing the explanation power, right? Because anyway, for the regression-based model, we know what are the impact of each feature as a result. But here in this machine learning-based model, we don't know the exact impact of each feature at all. But anyway, instead of losing those explainability, then we have actually a better result. And people kind of accept him by those good results without knowing the details about this model. So anyway, for this, let's just have a short break. Thank you for listening for the first part.